Okay, 5.8 related rates. I think that you will find this much more interesting and fun than optimization, but maybe I'm wrong, but I think that this is fun. So if you go into it thinking it's fun, that'll work out well. Okay, so in the beginning of the year, I talked about calculus is just change. Anything we're talking about, how something changes. That's calculus. All right, so we're going to be just looking into different ideas. Let's say, for example, Mortimer is growing at a rate of 3 inches per year. All right, so we're talking about his height. So we could say h is height. And the rate that he's growing, that's a derivative with respect to time. Okay, so he's growing, so he's increasing at a rate of 3 inches per year. Okay, if we're looking at my stock portfolio is losing 5 cents per day. So we could maybe say V is the value. So the rate that the value of my stock is changing, it's losing 5 cents per day. Now we normally don't talk about cents, so I'm going to write it in dollars. So I'm losing, okay, that many dollars per day. We could talk about the radius of a circle getting larger, okay, so let R be the radius. So dRT equals, we're talking about the radius, it's getting larger by 4 feet per hour. All right, and then we could also say the outside temperature. So I'll call T temperature. I didn't use a little t because I'm going to use that in a second. So the rate that the temperature is changing, it's dropping by 5 degrees Fahrenheit per minute, which is pretty quick. All right, so all we're talking about is just these rates. Somehow it's changing, okay? And we'll be specifically saying how. So let's draw a picture here. You could call it L length and width, L and W, but I'm going to call it X and Y. Okay, so the length of it and a rectangle is decreasing by 2 inches per second. So since my length is X, I'm going to write that down. X, all right, that's changing. It's decreasing by a rate of 2 inches per second. Okay, the width, on the other hand, dy dt, that is increasing by 3 inches per second. So what we're doing is we're looking at one particular moment in time because it's constantly changing. We're looking at one particular moment. All right, if you want, we could say it's like the snapshot moment, right? When the length is 10 and the width is 6. So we're looking at that, you can think of it like a camera. It's a snapshot moment. Right then, how fast is the perimeter and the area changing? All right, so for part A, how fast is the perimeter changing? That's what we're looking for. All right, so we got to find the perimeter first. Well, that's just 2x plus 2y. How fast is it changing? We're talking about taking the derivative with respect to time. All right, so dp dt equals 2 dx dt, so we're taking the derivative of x with respect to time, plus 2 dy dt. We're trying to figure out how the perimeter is changing at that specific snapshot moment of time, okay? So we could say when x equals 10, you could add when y and y is 6, you don't have to. So when x is 10, dp dt equals 2 times, well, dx dt is negative 2 plus 2 times 3. So dp dt is 2 inches per second. I'm going to write this and then I'll erase it. My pen's too big. All right, so as a summary, when x equals 10, the perimeter is increasing by 2 inches per second. All right, that's your summary statement. That's explaining what it is. Now I'm going to erase that so I have more space. All right, and I'm going to try to make this a little smaller. All right, maybe that'll help. Now, how fast is the area changing? So for part B, we're trying to find dA dt. Yeah, I'm not going to have enough room. I'll put it in the bottom. Okay, so dA dt. Well, we need to find the area first, right? That'd just be x times y. So dA dt equals the first times the derivative of the second plus the second times the derivative of the first. All right, and now at that specific moment when x equals 10, dA dt equals, so we have the x, which is, let me roll back up here, x is 10, dy dt is 3, y is 6, I believe, yep, okay, and dx dt is negative 2. So that's 30 minus 12 equals 18. So that means that dA dt equals 18 square inches per second. So when x equals 10, the area is increasing by 18 inches squared, 18 square inches per second. All right, so that's an introduction to this. We're looking at one specific moment in time, and we're trying to evaluate how other things are changing. All right, so now I'm going to just clear this out so I can start the next problem. Oh, that didn't work out at all. There we go. All right. So now we're dealing with a triangle, a right triangle, not just any triangle, it's a right triangle, whose sides are changing, okay? So here's my triangle, it's a right triangle. I'm going to call this X, call this Y. All right, the sides are changing. So at a particular moment, right, at the snapshot moment that we're looking at, X is 30 and Y is 40. That's our snapshot. This is my beautiful camera. All right. A right triangle whose sides are changing. Okay. If the shorter of the two sides, so that'll be my X, is increasing at a rate of 3 inches per second. Okay. And the longer side is decreasing at a rate of 5 inches per second. How fast is the area changing? All right. So we're looking for dA dt. So we're starting with our first equation. All right, and I'm gonna call that position. That's just our basic equation. Rather than say function, derivative, blah, 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 we'll call that our position function. All right, so then we're gonna take the derivative. All right, so first times the derivative of our second plus the second times the derivative of the first. At that very instant, that snapshot moment, okay, when x equals 30, dA dt equals 1/2 times 30 times negative 5 plus 1/2 times 40 times 3. All right, so that ends up being what, negative 75 plus 60, negative 15 inches squared per second. All right, so as my summary statement, I would say the area is changing. The area is, instead of changing, I'm going to say the area is decreasing this time at a rate of 15 square inches per second. All right, let's try the second problem. This time, how fast is the hypotenuse changing? Okay, so we're going to find dH dt. So my position equation, or my first one, is x squared plus y squared equals h squared. So then taking the derivative, 2x dx dt plus 2y dy dt equals 2h dh dt. So simplifying that, I could divide everything by 2, right? So I get x dx dt plus y dy dt equals h dh dt. All right, so you're going to have to find h. So at that snapshot moment, if you do 30 squared plus 40 squared and solve for h, okay, h is the square root of x squared plus y squared, you get 50, okay? So plug in those. So when x equals 30 in this case, so we have 30 times dx dt is 3 plus 40 times dy dt, which is -5, plus, or equals, sorry, h is 50 dh dt. So we get what, 90 minus 200. Okay, 90 minus 200 equals 50 over dh dt. So I believe dh dt equals negative, now I can't think. All right, so 90 minus 120, that'd be negative 110 divided by 50. So what's that, negative 2.2? D inches, we're talking about hypotenuse. Wow, what is that? Okay, let me write that answer a little bigger. So negative 2.2 inches per second. So we would say, as our summary, dHdt, okay, the hypotenuse is decreasing at a rate of 2.2 inches per second. You don't put the negative on there, you explain, it's decreasing. So again, I mentioned that, let me get my highlighter, this is easier. This is our position equation. So we're going to be relating that really soon. So then I would say that this part right here, this is my velocity equation. That's how you can think about how it's changing, okay, velocity. And later maybe we'll even go as far as finding acceleration. So last thing for today, just read through these 11 easy steps to solving a problem. All right, there's only 11, not a big deal. My favorite is probably number 11. So go ahead and read through these and try a problem or two, maybe 3, or dare I say 4 problems. That's just pushing it though, in your notes, and make sure you fill out a WISC.